Welcome back to the Lesson 2, Topic 3, Part 2. This is Sir Arvs. Come and join me as we tackle about the subtopics 2, 3, and 4. Subtopic 2, Compound Statement and Grouping Symbols. In the previous topic, we discussed that a compound statement is a combination of two or more simple statements connected together using logical symbols such as and, or, if then, and if and only if. Let's have the following examples. P. You get a promotion. Q. You complete the training. R. You will receive a bonus. Translate the following compound statement. A. P and Q implies R. P. You get a promotion. Q. You complete the training. R. You will receive a bonus. The logical connector between P and Q is and. Therefore, the first part will be you get a promotion and you complete the training. The logical connector between the quantity P and Q, then R, is an implication. Therefore, our final answer is if you get a promotion and you complete the training, then you will receive a bonus. B. If you do not complete the training, then you will not get a promotion and you will not receive a bonus. You do not complete the training is not Q. You will not get a promotion is not P. You will not receive a bonus is not R. The logical connector between not P and not R is and. The logical connector between not Q and the quantity not P and not R is an implication. Therefore, our final answer is not Q implies the quantity not P and not R. How about you try answering the following compound statements using these simple statements. P. Keisha's singing style is similar to Office. Q. Keisha has messy hair. R. Keisha is a rapper. Translate the following compound statement. A. P and Q implies R. I will give you 5 seconds to answer. Correct. The answer is if Keisha's singing style is similar to Office and Keisha has a messy hair, then Keisha is a rapper. B. If Keisha is not a rapper, then Keisha does not have a messy hair, and Keisha's singing style is not similar to Offie. I will give you 5 seconds to answer. Correct. The answer is not R implies the quantity not Q and not P. The truth value of a simple statement is either T or F. The truth value of a compound statement depends on the truth value of its simple statements and its connective. This can easily be illustrated by constructing the truth table. The truth table is a table that shows the truth value of a compound statement. Truth value of a conjunction. The conjunction P and Q is true if and only if P and Q are true. Truth value of a disjunction. The disjunction P or Q is true if and only if P is true, Q is true, or both P and Q are true. In other words, if it is AND, both simple statements P and Q must be true. Then the entire compound statement becomes true. If it is OR, the entire compound statement becomes true when one or both of its simple statements is or are true. Determine whether each statement is true or false. Letter A. 7 is greater than or equal to 5. This can be illustrated as 7 is greater than 5 or 7 is equal to 5. Since the logical connector is OR, either of the statement must be true in order for the compound statement to be true. 7 is greater than 5 is true. Therefore, the entire compound statement is true. Letter B. 5 is a whole number and 5 is an even number. 5 is a whole number is true. 5 is an even number is false. The logical connector is AND. But in AND, two statements must all be true. Therefore, letter B is false. Letter C. 2 is a prime number and 2 is an even number. The logical connector is AND. 2 is a prime number is true. 2 is an even number is true. Therefore, the entire compound statement is true. 21 is a rational number and 21 is a natural number. 21 is a rational number is true. And 21 is a natural number is true. Therefore, the entire compound statement is true. Letter E. 4 is less than or equal to 9, which can be illustrated into 4 is less than 9 or 4 is equal to 9. The logical connector is OR, which means that either of the statements can be true, therefore it makes the whole compound statement to be true. 4 is less than 9 is true, therefore the entire compound statement is true. The last letter. -7 is greater than or equal to -3, which means that -7 is greater than -3 or -7 is equal to -3. -7 is equal to -3 is false. -7 is greater than -3 is false. That makes our entire compound statement to be false. There are these quantifiers that we call existential and universal. Existential quantifiers include the words some, there exists, and at least one. Universal quantifiers include the words none, no, all, and every. So how do we negate these quantified statements? Negating the statement all x or y will become some X are not Y. Negating the statement no X are Y, it will become some X are Y. These are vice versa. Write the negation of each of the following statements. Letter A. Some airports are open. What will be the answer? No airports are open. Letter B. All movies are worth the price of admission. The negation is some movies are not worth the price of admission. Letter C. No odd numbers are divisible by 2. The negation is some odd numbers are divisible by 2. How about you try negating the following statements? Letter A. All bears are brown. 5 seconds. Correct. Some bears are not brown. Letter B. All smartphones are expensive. 5 seconds. Correct. Some smartphones are not expensive. Letter C. Some vegetables are not green. Correct. All vegetables are green. Application of symbolic logic. Claude E. Shannon wrote a thesis which applies symbolic logic to switching networks. It consists of wires and switches that can be opened and closed. These networks has been used in many electrical appliances as well as telephone equipment and computers. Subtopic 3. The conditional and biconditional. Truth value of a conditional. The conditional P implies Q is false if P is true and Q is false. It is true in all other cases. The truth value of a biconditional. The biconditional P if and only if Q is true if P implies Q is true and Q implies P is true. I know what you're thinking. Let us explore them slowly. We begin making the truth table. There are 2 simple statements P and Q, and each of these statements may have 2 truth values P and F. Thus, 2 for statement P times 2 for statement Q. We now have 4. And that 4 is the number of rows. If there are 3 statements P, Q, and R, that makes 2 times 2 times 2. That is 8 rows. Let us stick to 4 since there are 2 statements. We now begin putting truth values to the truth table. Since there are 4 rows per column P, we can say that there will be 2 T's and 2 F's. Next, for column Q, there will still be 2 T's and 2 F's. However, we must not forget to write them in a manner that no columns for Q that will repeat alignment with P. Now, we can supply the missing cells. Remember the rule for truth values. The conjunction P and Q is true if and only if both P and Q are true. That is, junction P or Q is true if and only if P is true, Q is true, or both P and Q are true. So, for the first column, P or Q. P or F. F or T. F or F. For the next column, P and Q. P and Q. For and, remember that both must be true in order for it to be true. F and T. F and F. Next, for the conditional. For the conditional, P implies Q is false if P is true and Q is false. It is true in all other cases. It means that the only way for the conditional to be false if we started with true and ended with false. So for P implies Q, we look for P, the end, Q. Starts with T and ends with F. That's the only way to make it false. The same way, conditional statement Q implies P. We start looking with Q, then we imply to P. So we start looking with a column for Q, then we look for the column for P. So T implies T is T. F implies T is T. T implies F is F. F implies F is T. For the biconditional, biconditional if and only if is true if P implies Q is true and Q implies P is true. Meaning, for these last two columns for implication, we look at if both of them are true, then the biconditional becomes true. So there you have it, the entire truth table for P, Q correspondence. Since you have the skills in constructing a truth table, it would be easier for you to identify the given statements, whether it is a tautology or a self-contradiction. A tautology is a statement that is always true. A self-contradiction is a statement that is always false. Identify whether P implies the quantity P or Q is a tautology or a self-contradiction. There are two statements, P and Q. Therefore, it will be 4-row table. We then start by solving the truth value of P or Q. Since the logical connector is OR, one of the two statements is true, makes the entire statement to be true. So true or true is true. True or false is true. False or true is true. False or false is false. Next is we compare the two statements. P implies the quantity P or Q. That is P and the quantity P or Q. Remember, it is an implication. The only way to make it false is to start with true and end with false. True implies true is true. True implies true is true. False implies true is true. False implies false is true. All of the answers are true. Therefore, it is a tautology. Identify whether P and the quantity, not P and not Q, is a tautology or a self-contradiction. We then start with not P. Not P is just flipping true to false and false to true. So, not P will be false, false, true, true. Next is we combine not P and Q. The logical connector is AND, which means that both of the two statements must be true to make it true. F and T is false. F and F is false. T and T is true. T and F is F. Next is the final statement. P and the quantity, not P and Q. That is P and the quantity, not P and Q. Remember that the logical connector is AND. Therefore, both of the statements must be true to make it true. T and F is F. T and F is F. F and T is F. F and F is F. All statements is always false. That makes it a self-contradiction. Symbolic arguments. Arguments. In this section, we consider methods of analyzing arguments to determine whether they are valid or invalid. Example: if Aristotle was human, then Aristotle was mortal. Aristotle was human, therefore Aristotle was mortal. Is this argument valid? An argument consists of a set of statements called premises and another statement called conclusion. An argument is valid if the conclusion is true whenever all premises are assumed to be true. And an argument is invalid if it is not a valid argument. There will be three procedures in determining the validity of an argument. The first one is to write the argument in symbolic form. Second, construct a truth table that shows the truth value of each premise and truth value of the conclusion for all combinations of truth values of the simple statements. And the third one If the conclusion is true in every row of the truth table, in which all premises are true, the argument is valid. If the conclusion is false in any row which all of the premises are true, the argument is invalid. Let's scrutinize the argument. If Aristotle was human, then Aristotle was mortal. Aristotle was human, therefore Aristotle was mortal. Our first premise is if Aristotle was human, then Aristotle was mortal. Our second premise is Aristotle was human. That makes our last statement to be the conclusion. Therefore, Aristotle was mortal. Remember that the step 1 is to make them symbolic, which means we have to change Aristotle was human into symbolic letter, which is H. Aristotle was mortal will be stand with M. Step 1. H implies M because the statement is if Aristotle was human, then Aristotle was mortal. Aristotle was human. It's H. Therefore, Aristotle was mortal was just M. So that is our first premise, the second premise, and the conclusion in symbolic form. An argument is valid if the conclusion is true whenever all the premises are assumed to be true. We continue with the step 2 in constructing the truth table. H implies M. Remember the implication? You must start with true and end with false to make it false. Therefore, true implies true is true. True implies false is false. False implies true is true. And false implies false is true. Now, H, you just copy the given. T, T, F, F. Then copy the given for M. T, F, T, F. Step 3. Remember that you must identify whether the conclusion is true when assuming that the first and the second premises are said to be true. And that is the row 1. The first premise and the second premise in row 1 is assumed to be true. Check whether the conclusion is true. The conclusion is true. Therefore, the argument is valid. How about you try answering whether the argument is valid or not valid? If I am going to run the marathon, then I will buy new shoes. If I buy new shoes, then I will not buy a television. Therefore, if I buy a television, I will not run the marathon. You may pause the video for you to answer. Okay, the answer is the argument is valid. Correct. That ends our Lesson 2, Mathematical Language and Symbol, Topic 3, Part 2. Thank you for joining in today's discussion. This is your presenter, Arvin B. Salera. Bye!